Hello, this video is about group 7, the halogens. We're going to start by looking at the electron configuration and then some of their physical properties. So the halogens are all in group 7, which means they have 7 outer electrons. They are the 5th element along in the p block, and that's because their outer electrons are in the p subshell, and they all exist as diatomic molecules. So we've got fluorine's electron configuration here. We've got 7 electrons in the second shell, and 5 of those electrons are in the p subshell. So pause the video and complete the rest of the table. So chlorine is in the next period below fluorine. So its highest energy or outer electrons are in the 3rd energy level or shell, and its outer electrons are in the p subshell, so 3p5. And then bromine is in the next row down, so it's got the same electron configuration as argon, and then 3d10, 4s2, 4p5. And then iodine is in the next row down, so the 5th period of the periodic table, and same electron configuration as krypton, then 4d10, 5s2, 5p5. So we're going to look at the atomic number of the halogens. We're going to have a look at the MR of the molecule of the halogen. So just pause the video, get your periodic tables and fill that information in. Okay, so we're going to have a look at some of the information in this table and look at some of the physical properties of the halogens. We're going to start by looking at the atomic radius. So as we go down the group, you can see that the atomic radius increases. So we are going to think about the reason for that and then write an explanation. So this is fairly straightforward. As we go down the group, we have more shells, more shielding, so there's going to be a weaker attraction between the nucleus and the outer electrons. Next we're going to have a look at the ionic radius. So if we compare the numbers in the green column compared to the pink column, the ionic radius is bigger for the halide than the halogen. So the atomic radius for fluorine 0.071 and for fluoride ion 0.133. So we're going to write an explanation for that. So this is because the halide ion has got the same number of protons but an extra electron, so more electrons than the atom. So the attraction between the nucleus and the outer electrons is weaker. So next we're going to have a look at the boiling point, and you can see that as you go down the group, the boiling point of the halogens increases. So on the next page we'll write an explanation for that. So the boiling point increases as we go down the group, and the halogens evaporate less easily as the boiling point increases, and we say that the volatility or the halogens become less volatile as you go down the group. That means they evaporate less easily. So the reason for that is because down the group the halogen molecules are larger, they have more electrons, so the van der Waals intermolecular forces that exist between the molecules are stronger, so more energy is needed to overcome the intermolecular forces between the molecules. So next we're going to have a look at the electronegativity of the halogens. And you can see that the electronegativity decreases as we go down the group. And electronegativity is the ability of an atom to withdraw a pair of electrons within a covalent bond. So our explanation for that needs to take into account the definition of electronegativity. So the electronegativity decreases down the group, and that's because going down the group there are more shells and more shielding, and the attraction between the nucleus and the pair of electrons in the covalent bond is less. Lastly, first ionization energy decreases as we go down the group. That's because there are more shells and more shielding as we go down the group, so the attraction between the nucleus and the outer electron becomes less. Therefore, less energy is needed to remove the outer electron when we do the first ionization energy.